Brian Hammermeister, Project 1 for ITS6250. You can see on the left here my diagram shows my IP addressing layout. I've chosen to use both IP networks assigned to me. For the PCs, I've used a 1064 network. I've used a 255.255.255.0 subnet mask, allowing 254 hosts per network. I like to keep my broadcast domains small. So router 1 is connected to virtual PC 1, 10.64.1.10. You can see the third octet matches the router number. And I've done that for all the virtual PCs. So router 2, 10.64.2 matches that router number. So all the PCs are .10, all the routers are .1. For the loopbacks and all the connections between the routers, I've used the 192.168.64 network, and I've used a subnet mask of 255.255.255.252, which allows 2 hosts per subnet. For the loopbacks, I'm just only need one of those, but for the links, that's perfect because I just need 1 host for each side of the link. So this is very economical, and it does not waste address space, and this is realistic to how you would approach it in the real world. If you look at my GNS3 diagram on the right, that matches my diagram that I've drawn in the package on the left. And I have got 5 routers in each, and I've got 5 virtual PCs in each. On the GNS3 diagram, I've actually put the gigabit interface so that you can see how it matches. Let's log into router 2 and show how it matches the diagram. I'm going to do a show interface brief. Okay, you can see here gigabit 10, 1064 2.1 matches the diagram right here where my mouse is pointing. Gigabit 20 on the router interface list, 192.168.64.2 matches gigabit 20 here on the diagram where my mouse is pointing. Gigabit 40, 192.168.64.5 maps to where my mouse is pointing here on the diagram for the interface gig 40 heading to router 3. And then finally gigabit 50, 192.168.64.9, that's where my mouse is pointing on the diagram here. That's heading to router 4. So you can see the way I've set this up, if you look at both the GNS3 layout and the diagram that I've created. The medium-sized company with 5 buildings where we have 1 router in each building, you can see here represented by both the diagram and the GNS3 picture. It meets those requirements, as well as there's at least 1 router that's connected to 3 other routers. So in my case, I've got router 2 connected to 3 routers, router 3, router 4. Only router 1 has 1 connection to 1 other router. RIP is already configured everywhere except for router 2, right here where my mouse is pointing. I'm going to demonstrate the lack of connectivity by pinging and trace routing from PC1. IP address of PC1 is 10.64.1.10. I'm going to try to ping from PC1 to PC2. Destination network unreachable. Also, if I do a trace route there, same thing, destination network unreachable. So router 2, I'm doing a show IP route for router 2, and it has no RIP routes, just direct routes. Activate RIP on router 2. You can see I've activated RIP process 1. I'm turning off summary routing. I'm making it RIP version 2, and I'm putting in my 2 networks here. Let's look at the routing table. See here you can see 3, 4 networks 3, 4, and 5 have been distributed by RIP. And you can see I've got some 192.168.64s distributed by RIP. Let's go to PC1. Okay, let's do some pings. We're pinging PC2. That's working. Let's trace route there. Now it's reachable, and you can see the path. Let's go to PC3. PC3 is now reachable from PC1 on the 3rd packet. So it picked up that route. Now let's trace route. And the trace route's working. You can see the path here. It's 4 hops. ping from PC1 to PC5. There it goes. And let's trace route. See, it's 5 hops away. Start the capture between router 1 and 2. Stop the capture. Doing the Wireshark capture between router 1 and router 2. And this is before and after I turned on RIP on router 2. You can see here router 1 with the address of 64.1 where my mouse is pointing is just sending out a multicast because it's using RIP version 2 of routes. So it does this a couple times, and it's advertising the 2 routes that it has, which is the direct link between them, showing here 10.64.1.0, and then the other one is its loopback address 192.168.64.24. Once I activate RIP on router 2, that's this packet here. What's interesting, I have RIP on here, but I don't have any network specified. So this is router 2 responding back to router 1 with, metric of 16 infinity. And then you look router 1 again, advertising its routes again, but it's actually between source address of router 1 and destination address of router 2. So it's responding to the request from router 2 where it was requesting routes where it didn't have any. And then this next packet is, now this is router 2 actually giving an update to router 1, and it's got all the networks in it that it knows from the other 3 routers, which is router 3, 4, and 5. And if you look at this, you can see 10.64.3, 10.64.4, 10.64.5. These are all the PC networks on the other 3 routers. And then these are all the other networks that are the links between the other routers and the loopbacks, the 192.168.64s, and there's several of those. I'd like to point out on, let's pick router 5. So right here where my mouse is pointing is the PC network on router 5. You see the metric is 3, right? So that's actually the cost, right? The number of hops to get over to router 5 from router 2's perspective. And then so that is the PC network off of router 5. And if you go to the bottom here, and I'm just going to pull up this network here, 192.168.64.40, that is the loopback on router 5, which is also cost of 3, metric of 3, hop count of 3, which it would make sense. It would be the same. And then you can look at some of these other networks here. 192.168.64.36 is the loopback on router 4. That's only 2 hops, right? So because that's a little bit closer. Create a link failure between routers 2 and 4, but before we do that, let's look at this trace route from PC1 to PC5. You can see here, based on my diagram, it goes from, the trace route shows it going up here from router 1 to router 2, the only path it can take, and then from router 2 over to router 4, because it selects 64.10, and then from router 4 to 5, it selects 64.18. Let's get a continuous ping going so we can watch the failure and then watch it recover. There it goes. Let's fail this link, which is a suspend. Okay, TTL is around 60. The millisecond time it takes for the ping is 4 to 7 seconds. See, it's still failing. Oh, just recovered there. As it's recovered, you can see the TTL is right around 60 still. And you can see the time it takes to ping is roughly the same as, 4 to 7 milliseconds. I'll go ahead and stop that ping. Route from PC1 to PC5 shows it going a different path now. It goes through router 3 here in the middle and on down to router 5, and you can see the IP addresses match up 64.6 right here on my diagram and 64.22 right here. Activate OSPF on router 2. I'm going to show you the routing table here. It's all direct routes. Even if I show you the OSPF specific table, there's 0 routes. All the other routers in the network have OSPF configured already in area 0. Let's activate OSPF on router 2. So OSPF process ID 1, area 0. I'm using this network command of all zeros and then all 255s. That activates OSPF networks on all those interfaces configured on the router. Let's go ahead and look at the routing table again now that I've activated OSPF. Okay, so now I have OSPF intra-area routes here. All the 1064, 1, 2, 3, 4, 5 are all the PC networks. And then you can see all the 192.168.64s are all the links between the routers and the loopbacks. And you can see here, when you actually specifically just look at the OSPF routing table, it gives you the routing table with the cost associated with each of the networks. Let's go ahead and ping from PC2 to show connectivity. PC2, I'm pinging PC1 here. Third packet, it picked it up. There you go, it's working. Let's go ahead and trace the PC2. You can see the path, it's just 3 hops. Let's go ahead and ping PC4. Timeout, third packet gets it. Let's go ahead and trace route to PC4. You can see there are 3 hops. And now let's go to PC5, ping it from PC2. Oh, there you go, third ping, and let's do a trace route. And that's 4 hops, that's further away. Start a Wireshark capture between router 2 and router 4. Here I'm showing a Wireshark capture of OSPF packets between router 2 and router 4. Router 2 is 64.9, router 4 is 64.10. Most of the packets are hello packets, which are each of the routers confirming adjacency to each other. Link state protocols like OSPF are very chatty. If I look at this advertisement update here, source address 64.9 coming from router 2, sent out to the multicast address. You can see here, if you look at the packet decode, that this is a LSA type 1, which means it's packets within the same OSPF area. And then if you look at what's in the update, you can see here it's advertising 1 transit network and it's advertising 2 stubs. Transit networks are networks that packets can traverse to get from point A to point B, whereas stub networks are dead ends. And these two here, these are coming from router 1. 1064.1 is the PC network on router 1, and then 192.168.64.25 is the loopback address on router 1. You can see here the metric for loopbacks is going to be 0. However, with OSPF, the metric for the other links that are associated with gigabit interfaces are a metric of 1. That's because OSPF defaults with 100 megabits as the default bandwidth, and if the bandwidth is higher than that, then it makes it a metric of 1. That's why you see that here. And again, if I look at another packet, I skip down here. This is coming from router 4, 64.10 to the multicast address, and it's also link state type of 1, and it's got 3 transit networks and 2 stubs. Again, and the originating router here that it's this packet originated from is from 64.33, which is actually router 3. See how this multicast from router 64.33 went out to all the routers in the same area. Test OSPF link failure. I'm going to show you a trace route from PC3 over to PC4, and here it is here. Trace route takes 3 hops. It basically goes directly from router 3 to 4. Let's get a continuous ping going. Okay, you can see it pinging. Let's go ahead and pause. Okay, you can see how it's timed out and it's waiting. We're waiting for OSPF to discover the links down and for it to reroute. Should be figuring it out here in a second. There it goes. It's recovered. You can see the TTL. Let me do a command Control C. You can see the TTL time to live is 61 here. and before that, the time to live was 62. So you can tell that it's found a longer workaround path. So now let's do the trace route again and see which way it's going. Okay, before I was 3 hops, now I'm 4 hops. So see which direction it decided to go. 64.5, this connection here. So it chose to go to router 2, and then on to 64.10, which is the link here, to router 4.